There's not like a good mix. It's either like really far out or really far in.
All right. So you move over the y squared, you move over the dx, and then you integrate. Anytime you're dividing by a variable, then it's going to turn into a antiderivative of that division. If that variable is a power of 1, it turns into a ln.
Really?
Yeah, anything that's a negative 1 in the denominator turns to ln. But in 2, turns to the negative 1. Remember, you're adding 1 to it.
I
so
thought you were talking about that one, my fault.
No, this one's going to turn to negative 1, yes.
Anything over a variable.
Yep, so you bring that up as that negative 2. The rule for antiderivative says you add back and then divide by your new exponent. So it'd be y to the negative 1 over negative 1. And then you get negative 2 over 2x squared. Now this is a plus c problem because they were indefinite bounds. So we have to add our plus c, and then this is where we're going to use that initial condition to plug in. So you get a positive 1 over y plus x squared plus c. So basically what I did was I just divided out the negative to cancel them, so they both became positive.
C, you don't have to worry about that.
No, 1/2.
No, we're going to solve for c.
Well, no, like you
The
change
C
all the
is
signs
1.
except C.
C is
Oh.
1.
Did I plug in the wrong numbers for c this time?
I just plugged it in before we even took anything.
All right.
Oh, it's because it's 1 over Y, so you just switched it.
Yeah, that's what I did.
You can do that?
Yes.
Really?
It's the inverse, right?
Well, if you do it out, like if you times by y and then you divide by x squared to get that on different sides, it makes sense.
Yep.
Wouldn't it be 1 over C though, or it doesn't matter?
That's what I was
C's
saying, like,
just a
C's
constant?
just
C's
like
just a
there.
constant, right?
Like you don't have to
Just a
switch, you never
constant.
switch
Said
sides.
yesterday it like absorbs it or whatever.
Yep, it gets absorbed in.
So do you have to plug it in the actual y equals equation? So like,
If you plugged it in where you did and then flipped it, you'd end up still getting the right answer because you have to take your 2 and distribute it out. And the 1/2 would end up becoming 1. Like if you manipulate it enough. All right, so today we're looking at exponential growth and decay. So exponential growth and decay is kind of like going back to the dy dt of ky days. So this is where you had a proportion and a constant of proportionality. So if you think back to your algebra days, this is where that k acted like a constant, and we were looking at exponential growth and decay functions over time.
The way you wrote constant is really messing with my head because it looks like an E, but I know it's an A.
Sorry.
It's really messing with me.
So to find the solution to the differential equation given these initial conditions, we're going to talk about y naught and t equaling 0. What?
Honestly, I mean, because it's cutting off all the words.
Why I made it small. And I'm going to write it. So you're going to take that dy dt equals ky equation, and we're going to plug it in here. So we're going to anti-derive that. So we're going to move the y's over to the dy's and the dt's over to the k, because k represents a constant, not a variable. So this is like 1 over y dy equals k dt, and then you're going to anti-derive. So this is the example I was hinting at, that the antiderivative of 1 over y becomes natural log of y. The antiderivative of k becomes kt plus c, because k is a constant, so it's kind of just like the variable's number on t. So the k is a constant, not a variable. How do you get rid of an ln? Because we need to solve for y. E both sides. So you get y equals e to the kt plus c. But again, we talked about the rules for exponentials. And if you have e to the kt plus c, it's kind of like the same as saying e to the kt times e to the c. But we know that e to the c is really just a constant. So e to the c represents our initial condition. So this is really like y equals c e to the kt, where c is the initial condition. Now, what do we know about a natural log's antiderivative? That if we don't know what y is, it's typically considered to be an absolute value. So previously I talked about how these were absolute values. What do you know about an absolute value? It kind of turns into a piecewise, right? So you have the positive and the negative. So what happens is that positive or negative kind of gets encompassed onto our c value. And a positive c is going to represent that growth that we're kind of looking at. The negative c is going to kind of give us an initial decay. So again, that c value is our initial condition, or it's the amount at time t equals 0. How do we know it's at time t equals 0? Well, if you plug 0 in here, e to the 0 power is 1. So that's how this is our initial condition, because this will turn to 1. So this is the initial condition. It's the amount at time t equals 0.
Now, is that stuff you have to write for an answer, or just to y is equal to?
If they asked you what the initial condition was, you would say what c is equal to. So if y changes at a rate proportional to the amount present, that rate proportional to the amount present is dy dt equals kt. Remember, derivative represents rate. So if it's talking about a rate proportional, it's talking about dy dt, and in this case, it's talking about dy dt equals kt. And our initial condition, well, what's our initial condition? We have two ways of referring to it. It's going to be that y naught or c. Oftentimes, you're going to see this look like something like y equals y naught e to the kt, or y naught, what?
Didn't we show that equation yesterday?
Yes, that's what I said. Today is kind of like the follow-up to yesterday, where now we're going to actually talk about, okay, what does exponential growth look like? What do they give you, and how do we look at this? Is going to be more word problems. Yesterday was a lot of, yesterday was a lot of just like straight problems. Today is a little bit of word problems. Okay? So it says the ratio of change of y is proportional to y. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of t at 3? So basically what we have to do is take into account this y equals y naught e to the kt. So what's my initial condition? Well, my initial condition is that at t equals 0, y is 2. So what do I need to solve for? Or how do I kind of plug that in? If t is 0, y is 2. So you get 2 equals y naught e to the k 0. What did we say about e to the 0? It's 1. So what's that mean about y naught?
It must be.
Okay, so now we're down to one variable that we need left. What variable do I need to know now?
Okay.
Okay, I need to find out what's the constant of proportionality. So I'm given a second initial condition. I'm given that at time 2, y is,
4.
so you plug 4 in for y, 2 in for t. We get 4 equals 2e to the case 2. So you divide both sides by 2. You get 2 equals e to the 2k. How do you solve or get rid of an e?
ln.
Yeah, you're going to ln both sides. So how do you get k by itself?
We divide.
So k equals 1/2 ln 2. I concur. So what's your exponential equation?
Y equals 2d. So 1/2 ln. How do you read that? 1/2 ln 2?
Yeah.
So like up 2 right like that. Just
1/2 ln 2. So now they've changed the dy dt a little bit on me. Instead of giving me a k, they gave me a,
negative 2y.
yep, that negative 2y. So that sort of changes the problem a little bit. What's that negative 2 represent?
Why not?
Mm,
That's slope.
it's the k, right? Because the equation is dy dt equals ky. So that means that k is negative 2. It's the constant of proportionality. My y naught comes from the time t equals 0. So what's my y naught?
1.
1. Because at t equals 0, the y value is 1. So that means my y naught has to be 1. Because whatever the y value is when t is 0 is your y naught. So now I know y naught. I know k. So do I know my equation? Y equals 1 e to the negative 2 t.
And that's rate of change. Right?
What?
That's rate of change.
Yes. Then it says, what is the value of t when y equals 1/2? So this time I'm looking for t. So y is 1/2 equal to e to the negative 2t. So how do you get rid of your e? So you ln 1/2 equals negative 2t. So here's something cool. The ln of 1/2 is really like the ln of 1 minus the ln of 2. What do you know about the ln of 1? It's 0. So the ln of 1/2 is really negative the natural log of 2, which kind of makes this a little bit nicer because t is considered negative ln 2 over negative 2. So what happens? Your negatives cancel. And oh my goodness, I got the same k value as the previous problem. ln of 2 over 2.
I thought this is t we solved for.
We did, but we just still got that ln of 2 over 2. So ln of
Oh, so that's the k.
yeah, but this is our time. But it's just ironic we got the ln of 2 over 2 twice. And the reason for that is ln of 2 over 2 is going to represent half of decay. So your problem will be at half of its decay at that time point. And that's the next thing we're going to look at, with the radioactive groups in decay. So go ahead and flop over to the slide that looks like that. So radioactive decay is the amount of radioactive element left after time t. Why is my k value negative in this problem?
Because it's losing stuff.
Because it's decay, because it's going down. So the k value will be negative. The half-life is always going to be represented by the equation time equals the natural log of 2 all over k. Half-life will be represented by time equals the natural log of 2 all over k. That's just something, if you get a problem and it involves half-life, that's all you need to know. So if it says, when will the half-life of this occur? It's ln of 2 divided by whatever your k value is.
K is the amount of material? Or?
K is the proportion constant. K is the rate of change with respect to time.
So you have to use that other equation to find K and then plug K in.
Sometimes. And that's what we're going to do in the next example. Okay, so it says the rate at which a radioactive element decays as measured by the number of nuclei that change per unit of time is proportional to the amount of nuclei present. So, Chernobyl, real place in time. Somewhere you're not really supposed to go and spend time at because there's still radioactive substances there. So it says, suppose that 10 grams of this isotope were released in the Chernobyl nuclear accident. How long will it take 10 grams to decay to 1 gram? It has a half-life of 24,360 years. So, that means we know what? What does this years represent?
The time when it's 5 grams.
Yeah, this represents the half-life. So that represents the time at which its life is half. So half-life is ln of 2 divided by k. So I can use that half-life to find my k value. So my k value is equal to the natural log of 2 divided by that 24,360 years. What was the initial amount present? 10. So what's that 10 going to represent?
Why not?
So y naught is 10. I found my k. Now what doesn't k have in this case that we know it needs?
Negative.
A negative. Because we know this is decay. So y equals 10 e to the negative ln of 2 divided by 24,360 t. What am I looking for? What is the question really asking?
It's time when y is equal to 1.
Yeah, so I need the amount at 1. So it's 10 e to the negative ln 2 all over time. So you divide by 10. And then you ln both sides. But again, ln of 1 is always going to be
0.
So anytime you have an ln with a fraction, it just becomes negative the denominator. So it'd be like ln of 1 minus ln of 10, so you get negative ln of 10 equals multiply by its reciprocal, and that gives you t. Okay, your homework is in your book. Sorry about that. Page 357, 1 to 14 all. So not that many. I will definitely throw out a Delta Math. Delta Math will just be kind of bonus.